Hey everyone, welcome to this Forge College Explainer. If you've been following along on our journey from EVM to SVM, you know we've been deep in the trenches porting token standards over to Solana. Well, today I want you to grab your metaphorical hard hats and, your technical pens because we are drafting an engineering patent. We're building a highly efficient blueprint for scalable, reusable token architectures. So let's just dive right into this patent schematic, shall we?
All right, here's the docket for today's patent filing. We're going to start by moving from single flows to massive factories, then check out account layout architectures, smart instruction routing, using PDAs as authorities, translating it all into a code blueprint, and finally, sealing up our design. It's a packed docket, so let's get building.
Section 1. From flows to factories, scaling beyond a single token.
So, in our last lesson, we walked through how to execute basic single token flows. Minting, transferring, the absolute fundamentals. But now we really want to scale. We're graduating from handcrafting one isolated token to engineering a massive, reusable factory. And honestly, this right here brilliantly illustrates the core architectural difference between Ethereum and Solana. Think about the EVM world for a second. If you want 1,000 different token collections, you usually have to deploy 1,000 separate smart contracts. It's literally like building a brand new factory building just to produce a different color of the exact same car. Makes no sense, right? But on Solana, our patent relies on reusable programs. We deploy one single, highly optimized architecture exactly once, and it can securely manage infinite token instances. Infinite!
Moving to Section 2. Account layout architectures. Where exactly does the data live?
When we're drafting this factory blueprint, the absolute first major structural choice we have to make is deciding exactly where our data lives. This one choice dictates how complex our validation logic is going to be and, crucially, how we handle Solana's rent-exemption storage costs for all those infinite tokens. Look at the left side of our blueprint here. We've got the lightweight wrapper pattern. You can think of this as a lean, mean, rent-exempt machine. It uses super minimal storage, holding just a tiny descriptor, and, this is key, it delegates all the heavy lifting, like tracking balances and supplies, over to the standard SPL Token program using cross-program invocations, or CPIs. It's basically perfect for something like an NFT marketplace handling hundreds of simple collections. But then, on the right side, we have the managed state pattern. Now this is your heavily guarded VIP club. It uses way more storage because it centralizes all that complex validation logic directly inside your program. So if you're building, say, an enterprise regulatory token that needs strict on-chain KYC checks, complex transfer restrictions, or, an instant pause button, you are absolutely going to need this managed state.
Let's actually look at the engineering spec sheet for that lightweight wrapper pattern. Check out these highly optimized numbers. Our token descriptor PDA, it's a mere 200 bytes. That just holds the mint public key, the decimals, and a seed for the admin. Super small. The metadata PDA size, well, that's variable depending on your URI pointer, but the actual SPL mint sits at a tiny 82 bytes. By keeping this on-chain footprint exceptionally small, we're minimizing the SOL required for rent exemption. Basically, it makes it incredibly cheap to just pump out new token instances right off our factory line.
All right, Section 3. Smart Instruction Routing, the traffic cop of Solana.
So now that we have our data structures all laid out, we need a bulletproof way to direct incoming commands. The crucial concept here is the instruction discriminator. I want you to think of this discriminator as the flashing siren or the specific hand signal that our traffic cop uses. It's essentially just a small tag, maybe a single byte or a short enum, sitting right at the front of the incoming instruction data. By using a tag dispatch or modular dispatch system, the program reads this tag and bam, instantly routes the command to the correct handler module. It's like sending a mint request directly to the minting department. Doing it this way keeps our program entry point perfectly compact, and it leaves us plenty of room to register new operations down the road without, completely breaking our carefully crafted architecture.
As we design these routing systems, I really want you to internalize this quote straight from the source material. It says, think in terms of what must be rent-exempt and always present versus what can be ephemeral or recreated. Seriously, this is our golden engineering rule here. Think about temporary escrow accounts during a complex token swap. Those are ephemeral, right? Just let them vanish when the job is done. But the core supply rules and decimal precision for a token, those must be always present. Secure them safely.
Moving on to Section 4. PDAs as program authorities. Look, Ma, no private keys.
Yeah, on the construction side, I actually do call this the look-ma no private keys approach. Because in our engineering patent, relying on human beings to manage live private keys for token operations, that is a massive liability. So what do? We simply design them completely out of the equation. Enter the PDA, the program-derived address. These PDAs are stable, completely program-controlled addresses that serve as the undeniable authorities for tasks like minting new supply or administering the token. By using a PDA, we literally remove the need for external private keys entirely. The program's code itself algorithmically signs the authorization. It's brilliant. This dramatically simplifies complex multi-sig approvals, and even better, it guarantees that if we upgrade our program later, we don't face that absolute nightmare scenario of trying to rotate private keys for custodial accounts. And while we're establishing these super secure, keyless authorities, we absolutely must enforce a strict separation of state. We rigidly separate our immutable configuration, stuff like token decimals and the initial PDA seeds that will never, ever change, from the mutable runtime state. That's things like your current token supply or emergency freeze flags. Now, why does this matter so much? Because when you inevitably have to upgrade or migrate your program, and you will, you can leave that delicate configuration completely untouched and only migrate the runtime state to a new PDA. I'm telling you, it turns a massive headache into a totally seamless transition.
Section 5. The Code Blueprint. Translating specs to Rust pseudocode.
Okay, chief engineers, strap your safety goggles back on because we are diving straight into the code. We've talked a whole lot of architectural theory, so let's translate these specs into some actual Anchor-style Rust pseudocode. Let's see exactly how our patent looks when we deploy it in production. Right here, we have our token descriptor struct. This is the absolute beating heart of our lightweight wrapper pattern. It holds the SPL mint public key and the decimal precision. But pay really close attention to that admin bump field. Storing the cryptographic bump directly in the struct, that is a very clever engineering trick. It allows the program to instantly reconstruct the PDA later without having to waste precious compute resources recalculating it from scratch. Basically, it stabilizes our PDA derivation across any future program upgrades.
Now let's actually look at how our instruction handler processes a request. Let's say a request to mint new tokens. Step 1. Validate that the descriptor matches the provided mint. This is an absolutely critical security check. It proves the descriptor is mathematically bound to that specific SPL mint account, which entirely prevents an attacker from trying to cross-contaminate and mint tokens into some unrelated collection. You don't want that. Step 2. We use our descriptor and that clever little bump we just saved to perfectly derive our PDA seeds. And finally, step 3, we perform the cross-program invocation, the CPI, to the standard SPL token program, injecting our derived PDA seeds. That way, the Solana runtime can securely sign the transaction on our program's behalf.
And finally, Section 6, finalizing your design, sealing the patent.
All right, we have designed the factory line, so let's just quickly review the final checklist for your engineering clipboard. First, consciously choose your account layouts based on your specific needs. Are you going for the cheap, highly efficient lightweight wrapper, or the heavy-duty, rule-enforcing managed state? Second, route smartly. Always use those discriminators and strictly validate those account bindings before you fire off any CPIs. Third, utilize PDAs. Create stable, keyless, and wonderfully upgrade-friendly authorities. And finally, always separate your immutable configuration from your mutable runtime state. That's going to guarantee you painless migrations down the road.
Before we roll up the drafting paper today, I'm going to leave you with a provocative engineering question. How will you adapt this exact blueprint to add a mandatory pause flag for a highly regulated enterprise security token? Think about how you'd separate that new state and route those checks. We are actually going to tackle that exact challenge in our next explainer on lifecycle, upgrades, and preparing for security tokens. Oh, and by the way, this explainer was brought to you by Forge College. To dive deeper into these engineering challenges, see more real-world code examples, and aggressively level up your Web3 development skills, make sure to visit our educational hub at Forge College. Keep building, stay curious, and I'll see you in the next explainer.